So now we are talking about, first we start with a continuous time. Continuous time is what? We have a round bracket t, that's our continuous time. And we will figure out that even the discrete time, rectangular bracket n, the property will be pretty similar. That's what we see it. First property. So you may hear similar thing in linear time invariant system also. So you may feel some similarities. So in case of Fourier series, in Fourier series there are several properties which we can use them very usefully in homework. So first property is linearity. Linearity is what? They can be multiplied. The constant of multiplication will come out from the bracket. Also, they can be added. So in case of linearity, that means when x is a periodic signal and ak is corresponding Fourier series. So ak will be looks like what? ak will be looks like t over a period xt exponential minus j omega 0 kt dt. That's the definition of ak. If you put y in here, then corresponding Fourier coefficient will be pk. So let's say that coefficient of x is ak, coefficient of y is pk. If you do that, if you want to know the Fourier series coefficient of another function, say xt plus yt, with a constant. ab is a constant, not a function. Then this one has Fourier series coefficient, say ck, which is large A times ak plus large B times bk. That's the linearity, right? So means that if you know the Fourier series coefficient of each function, you can directly derive Fourier series coefficient using this property. The derivation is pretty straightforward. Derivation is pretty straightforward because if you put ck, you will try to find ck. How to do it? Well, you put that, put ct in here, right? And then let us change this one to this signal, which is ax plus by exponential minus j omega 0 kt over dt. And then integration is linear, right? You can divide them. You can divide them that ax exponential plus by exponential. And then we can take this a out from this integral. We can take this b out from this integral, which is this one will be our ak. This one will be our bk. So it will be ak plus bk. That's how the function goes. So this is a very straight proof, right? Say that if you have ak, bk, then you can just multiply by constant. There will be the corresponding Fourier series coefficient. The second property. Too fast? Second property, time shifting. So every claim starting from them, okay, xt has Fourier series coefficient AK. That's always the claim. Then, what about x t minus t0? What about this? The answer is AK exponential t0 something minus j omega 0 t0 hopefully times k. That's the answer. Why? Because let's have a derivation for a minute. Let's do that again. Say the Fourier series coefficient of this one is bk, for example, and put the equation one more time. Now we put t minus t0 exponential minus j omega 0 kt dt. Right? That's the definition of the Fourier series coefficient. So we try to find it. Now, we assume t minus t0 is tau. One more definition on it. And then, the period order will not be changed. Right? The period of t and period of tau will not change. The period over one period. So let's put that one period, say x tau times exponential minus j omega 0 k times actually t, which t equals tau plus t0. So tau plus t0 dt. I'm sorry, d tau. Right. Tau. And dt equals d tau. No polarity change. And then we have like this xt, x tau, exponential minus j omega k tau d tau. This is coming from here. Okay. And what about here? We can take this one to outside because this one is actually ej minus j omega 0 k t0, right? This one don't have any relationship with tau. Sorry, this is tau. This one don't have any relationship with tau. So we can take this one to outside. We can take this one to outside. So the answer is, and this one is AK, right? Fourier series of x. So we can think them as exponential minus j omega 0 k t0 times k ak, which is shown right here. So there is a basic derivation, which is also shown on here. So one interesting thing here is, if you know, you can use this one like this. If you have, okay, we already derived cosine t in last lecture, which is pretty straightforward one. And the question is, okay, we want to have what is cosine t minus t0? What is it? Then, of course, you can put it here, solve the exponential, and try to find a solution. You can do that. However, if you already know it, if you already know the answer, which we derive last time, should be, I'm not sure, probably like this, right? Okay. Something like this. To solve this, we have to put this one, change the cosine to exponential, do the integration, and blah, 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 take some time. But if you already know the answer, you just multiply this one by e minus j omega 0 t 0 k. That's it. You don't have to go through the calculation again. So if you know the property well, you can simplify your effort to find the solution. So please understand, please remember the properties as much as you can. So this properties is not only talking about property of Fourier series, but try to give you a easier way to find the answer. So second property here is, if you do the time scaling, if you shift this one by time, they will be multiplied by exponential. But one thing to make sure here is, when you remember that, always confusing is polarity. This is plus, this is minus. It's always confusing, so please make sure that. So we have to do with linearity and time shifting. Now what? Time reversal. Say we want to have, this one is still claimed. This is the same assumption we have. Say we have this. What about this? What is it? Minus t, time reversal, reversed by time. What is it? The answer is a minus k. How you solve it? We put again x minus t exponential minus j omega 0 kt dt, and let's assume minus t equals tau, and this one becomes what? Exponential minus j omega 0 k minus tau, and this one becomes what? Minus t tau, right? Is it? Nope. So we can think that, okay, what if you just do that over a period, and then we can assume that this k and this minus k combine together and say minus k is new, say, m. We can say this one becomes minus m j omega 0 tau d tau, because even though you put minus, say that you are minus half to half, then even though they reverse, they were the same. So what this one looks like, they're exactly ak. But note that this one is actually am, which is, in here we assume that m is minus k. So we can say they are minus k. That's one way you can do it. Another way you can do it here is more straightforward one. Say that, okay, not finding the coefficients and using the definition of Fourier series. There's a definition of Fourier series, right? We try to find what is ax, a minus t. Then let's put minus. Exponential, now j omega 0 k minus t. And then we do it again, say m is minus k. Then this one becomes what? A m exponential what? J omega 0 m t. Right? We observe this minus to this k, define new variable m, and use this. Of course, in here they become minus infinite to infinite. They becomes, this minus infinite go to infinite because they're minus. This plus infinite go to minus infinite, and they are same variable, except that this is actually minus k. So we can say that ak equals minus ak. So likewise, in either cases, we can figure out that the output of time reversal will be looks like this. Questions? topic number 4, time scaling. So we're starting with linearity. We talk about the shift by time. We talk about time reversal. Now what? We talk about time scaling. Scaling, meaning that we scale by time. Say, we have an original value, we scale by time. That's how things are going. And what's the output? Surprisingly, they are the same. Surprisingly, they are the same. How? We put them here. For detail, for this one, if you solve each by each, we have to consume a lot of time. So let's skip on this for a minute. So in time scale wise, we start on linearity, time shifting. They have minus j omega 0 t0. In reversal, they have minus k. In scaling, surprisingly, they are still ak. What about multiplication? Multiplication is what? Say another assumption here is yt. If you have yt, their Fourier series coefficient is bk. Another concern. This one is similar to the convolution. Convolution, remember that we briefly introduced that in time domain convolution, they becomes multiplication in frequency domain. Multiplication in time domain, they become convolution in frequency domain. We briefly introduced that. This is very similar to this relationship. If you have xt times yt, what will be their Fourier series? Then they will be similar to the convolution. Sigma ak bk. What's the convolution? What's the convolution? Having some variable here, having some, say, I in here, and something minus I, and which one becomes, this one becomes hk, something like this. So if you try to find value at k, you pick one of them, put I, one of the new variable, other one, say k minus I, say minus infinite to infinite. That's very similar to convolution. So in here, we have multiplication as an input. And then we can think them, they become a convolution, and they transformed. The convolution is what? We pick one of them, put the thing we want to find out is k. K is our output, corresponding to our, remember that, yn equals sigma, k equals minus infinite to infinite, xk, h and minus k. That's the convolution, right? This one is similar to that. In here, k is not our variable. Now we put a new variable k, say I. And our time scaling variable is n. In here is k. So k here corresponding to n here. I here corresponding to k here. So we put I instead of k in here. Put k minus I instead of n minus k over there. So the shape, how it looks like is exactly overlapping. And we are adding from minus infinite to infinite. So it's similar to the claim that we have multiplication in time domain. When you do the Fourier series, they change to convolution. Okay, convolution of these two variables. What about conjugation? Conjugation symmetry, meaning that we already know xt is like this. What about conjugate of xt, star of xt? What happens? Then, ideally, in generally speaking, we already derived in the beginning of the lecture. We already used this property when you derive this Fourier series coefficient. You already used it. So let's go to 14. There's the normal case. If xt is real, what happens? Then xt and conjugate of x will be the same, assuming that x is bj. Conjugate of x will be a minus bj, which is actually different. However, if x is real, then bj will be 0. Therefore, conjugate will be still a. Therefore, real and conjugate of x will be the same in case that xt is real. So, in case of that, what happens? A minus k equals a conjugate. This one is called conjugate symmetric. Conjugate symmetric. So in short, too fast? Fast? Too fast? Okay. Should we go back a little bit? So let me remind the property one more time, and then we can speed up. So by far, let's see how many properties do we have. Okay, we have one more property, then that's it. So by far, we have introduced 1, 2, 3, 4, 6 properties. Those properties is similar to what we learned in linear time invariant system, but this one does not only describe the system, but also help you simplify your calculation. First one is linearity. We say all of our claim is we assume that x has a Fourier series coefficient ak, y has Fourier series coefficient bk. That's basic assumption. If you have linear system, which is shown in the slide. If you have AK and BK, if you want to find large A constant times X plus large B constant Y, is the Fourier series coefficient is simply multiplying the constant by the Fourier series coefficient of X, multiply constant by Fourier series coefficient of Y. So the linear series is hold. And also, in case of time shifting, problem number 2, if you shift the signal by time, that means in time domain, there is a signal. If you shift the signal by t, the shift signal, then there will be coefficient times e minus j omega 0 t0 times k. So you can think them in the way that exponential minus j omega 0 k, which is a typical thing you can find out, times amount of shifting. One thing you have to be careful is polarity. Basically, there is a minus. Sometimes you have equation that is plus, sometimes you have equation minus. So one thing to make sure here is, in time shifting wise, from time to frequency, not frequency, time to some transformation, you typically has same polarity in here, from here to here. If you go later, we'll learn from frequency domain to time domain, they often has this minus become plus. So this is sometimes makes you confused, but if you think about the direction, if you think about the direction of the transformation, they have very similar property in all the transformation. Okay, so one thing you can see in here, from time domain to a kind of free or transformed signal, then you have minus in time domain, time shifting, then they become minus also in here. If you reverse by time, meaning that if you reverse the signal by time, then the property will be A minus K. So there will be minus in here. If you have time scaling, which is they multiply by time, which is time scaling, then the output will not be changed. So if you already know AK, if you want to know x2t, for example, the output will be the same. Topic number 5 means if you have x and y corresponding to AK and BK in Fourier series coefficient, if you want to find out the Fourier series coefficient of xt times yt, the new function, then you do something similar to the convolution. Convolution is what? Convolution is you try to find the value of y when n the variable is n. N is the variable. Say, if you want to find the y value when n equals 1, for example, you put 1 in here and change a variable k from minus infinite to infinite, multiply each k, multiply this value by each k, and add them from minus infinite to infinite. That's how you find out the convolution. This one is similar to the convolution. This one, the only difference is the variable, the notation changed slightly. So if I put them like, okay, let's find out Hn, for example, using those two. Then this one is similar to this. Say to find Hn, we pick one of them, put k, and then the other one becomes n minus k, and add from minus infinite to infinite. That's the same. This is convolution, right? But in here, we have different notation. Just the symbol is different. Similar structure, same structure actually, but symbol is a little bit different. Now we have this one, initial one is k instead of n. So let's change this n to k. And then this k and this k overlaps. So let's change this k to I, your new variable. And this n becomes k. And after that, without any cases, this one becomes hk. To find h when k has certain value, we add I. I is new variable. I is not j. I is not j. It also have a variable. Say we have I, k minus I from minus infinite to infinite, which is same structure with the convolution. That's what we say. In case of conjugate, conjugate is what? xt is a plus bj. Conjugate of x, this is complex signal, that means b minus j. If you already know the Fourier series coefficient of xt, if you want to know what is x star, x conjugate, if you want to find Fourier series coefficient of this one, there will be star minus k of the Fourier series coefficient of xt. That's a property. We already derived why this y looks like this in the beginning of the lecture. When you derive the Fourier series coefficient, we already derived that. It will look like this. If xt is real, that's a very special case. In this one, so this one is special case of this case. This one, This one, we have A and B. A and Bj, that's still valid. If X is real, we no longer have Bj case. That means X and X conjugate will be the same. That's the case. In this special case, when xt is real, then we can define them like this. There's addition to it. So this condition is a special case of this. That's how we derive by far. So what this one shows by far here is, if you already know Fourier series coefficient of x or Fourier series coefficient of y sometimes, then without doing the calculation, without doing those t over 1 over a period xt, some function, to find the Fourier series coefficient, we have learned that we have to put the function, do exponential minus j omega 0 kt dt. We solve this integration. That's how we find the ak or bk by far. But we cannot do that all the time. That's really time consuming. So assume that we already know this value in x or this value in y. And try to find something similar. Say, okay, you want to have xt minus t0. Without doing this calculation, we just multiply this ak we already know about by this variable. Then that's it. That's output. If you want to know conjugate value, you put the minus k and you put the conjugate of this ak. That's the major claim, major reason we learn about this property. We don't want to go through this calculation again. We already know that, we want to simplify the calculation. So question. 풀어볼까요? 자, 이거는 하기 쉽다. So x alpha t is what? Now exponential a, say bk minus j omega 0 So before we move on, let's define the relationship one more time. xt equals formation ak exponential minus j omega 0 kt ak equals 이거는요 끝나고 설명해 줄게요. 시간이 좀 오늘 숙제 때문에 좀 나가야 되거든요. So I will solve this case. I will solve this case at the end of the lecture because we have to speed up a little bit to help you to solve the homework. So once the class is finished, please gather if you have questions regarding this one. Other question other than this. Okay, so let's move on. Stockholm, are you okay? I think you have a question. I think you have one. No, you're fine? Good. All right, so we have now, this one is slightly similar to linear type invariant properties. Now we are introducing one unique property existing in Fourier series. Parseval's relationship. Parseval's relationship. Let's erase this. this is a very unique case because this is a relationship. Average over a period, and now we are not x. We are adding absolute value of x square dt equals. So we are not using x. We do the absolute value of x square and average it. So we are averaging not x, but absolute value of xt square. We are averaging this whole function. And that is summation of minus k minus infinite to infinite ak is. This one is, how to say, looks unfamiliar a little bit, right? But has some physical meaning. Let's talk about the physical meaning, other than just remember it. I'm starting with the claim that, okay, this side is, you need these equations to solve the problem. I think one of the homework is, say, function x has property number 1, 2, 3, 4. Find what is x, something like that. To solve it, you need this property. So this one, I claim that there is an average of a function. And the function is what? Absolute value of this. This one you can think them average power. We're adding all the power over a period. What about here? AK, what is absolute value of AK? AK, you can think them as the amplitude. Of course, A can be complex. A can be complex, but in Fourier series, they can be viewed as there's a Fourier series. So you can think this AK as some kind of amplitude, the amount of each frequency component. AK1 corresponding to how many the frequency component omega 01, omega 0. AK2 has how much the component, how much the component occupies in X. So this AK square is similar to that, how much the AK itself represents how much the amount of each frequency component in X. So this AK means that, let's say, so let's claim one more time. AK means the meaning of AK, even absolute value of AK means if you plot it in frequency domain, I'm sorry, let's forget the frequency domain. Now we claim that there is a arbitrarily repeating signal. Assume we are repeating, and in Fourier series we can say that we can divide them into fundamental frequency omega 0, 2 times omega 0, 3 times omega 0, omega 0, 2 omega 0, 3 omega 0, blah 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 blah. Frequency Fourier series, we claim that we can change this one signal to a set of sine waves having amplitude of each one has different amplitude, some kind of amplitude. Of course, it can be complicated, complex number. This AK represents how much each frequency component occupies in x. If this is 10, this is 1, means that this one has 10 times occupation compared to 1 time occupation. We can think them as, okay, this frequency component is more dominant compared to this frequency component. So this AK not only just gives you some idea that how to change the signal, but also corresponding to how much each frequency component occupies the x with x. So if you have absolute value, they're corresponding to amplitude, right? They're corresponding to how much amount, how much it occupies. And then what? If you add them all together, say that, that means we are adding the amount of omega 1, omega 0. We are adding amount of omega 0, amount of 3 omega 0. So we are adding the amount of this, amount of this, amount of this, and keep on going on. That means this one can be average value of the amplitude, I mean the power. Power of whole signal is the power from here, which is same to after you divide them to each frequency, sine wave having each frequency, and then add each one's power individually, get it, and add them together, which is here. They were the same. That's the physical meaning over here. Once again, this one is more like total average power. This is average, right? This is average. If you have one signal, which is periodic signal, if you try to find the average power of this one, you can put absolute value square together power, right? This power, and then do the average over one period. That's one way you can do it. Also, you can do that. You can change this one signal to a set of sine waves. That's a Fourier series. So we do the Fourier series transformation here, and then add the power of each frequency component. Add the power of each frequency component. Then, ideally, as this one is divided into sine waves. So if you add all the power, then they should be same. Okay, because if they are same signal, basically. So that's what this equation shows. Average power of the signal itself will be same to the power of component amplitude of each frequency. If you add all together, they will be the same. Why we are not doing average over here? Because in Fourier series coefficient, we already have average. Remember? Exponential height. So we already have average over here. So we are not doing average in here. So in short, like last sentence, thus total average power from the signal is same to summation, addition of additional power, average power in each component, which is very physically right here. In short, they have this is possible relationship. Physical meaning is original signal and the transformed signal, their power is the same, which is very physically true. So this is the last sentence we learn, Marx property we learn, possible relationship. Absolute value square power of original signal and then average it is equal to sum each component. That's the possible relationship. So this slide actually you can see that in your textbook. There's a table 3.1 in your textbook summarizing most of the properties. We have linearity, time shifting, we have linearity, time shifting, frequency shifting, we do not tell it. Conjugation, time reversal, time scaling, we already have it. And then convolution is possible. Convolution, remember that? We have convolution here, they just change the multiplication. Similar to here, we have a multiplication, they change similar to convolution. And if you have a differentiation, you have an integral, then they will change to different one. Finally, we have a possible relationship. I think one of you asking me this question that what happened to even function? Why have the odd function? Here's property over here. The special case that then when xt is real, we learn that they have this property. AK will be a star of minus k, which has this property. If x is real and even, then AK will be real and even. When xt is real and odd, then AK is purely imaginary and odd. So a little bit different, right? And if you want to find even part of x, EVx means only taking even part of x. That means the real part of AK, they corresponding to real part of AK. If you take odd part, they change to purely imaginary. That means if you have odd part of x, they become purely imaginary part of AK. Okay? Once again. Now assume xt is real. If xt equals even, they go to, in AK, they becomes a real part. If xt is odd, they go to purely imaginary part. Meaning that if AK has A, Bj, this one becomes A. If this is even, it becomes B if this is odd. So if you divide xt, some xt can be divided like they have an even property plus they have an odd property. If you change this one to AK domain, then this part would become the real part of AK. This part becomes the imaginary part of AK. That's how the equation says. So if you know the table, then you can simplify your calculation a lot. So this is summary of today's lecture. Questions? Okay, so let's bring in one example. I will give you a slide later. Let's bring in one example to use this. So this is not given yet. But let's solve one example to using this property first. So question is, okay, let's find Fourier's coefficient of impulse train. Impulse train is what? T minus kt minus infinite to infinite. Say this is our x. This one is something like if a time domain is 0, there's delta function at 0 and k equals 0. When k equals 0, when k equals 1, there's here. When k equals 2, the delta function. When k equals minus 1, and delta function, and blah blah blah. So we can think that this is periodic signal. From here to here, this is a set. It's a set of periodic signal, which is keep on repeating. This set is repeating by every t. Okay, so remember, Fourier series is only valid in periodic signal. They are not valid in not periodic signal. So if you have only one impulse, this is periodic signal? No, this is not periodic signal. This is not repeating, right? We cannot use Fourier series in this case. But if they are keep on repeating by a period of t, then it's possible to use it. So to represent this, we want to have, this is what? Delta t, right? This is what? The first one is delta t. The second one is what? Delta t minus t. Is following? Because they are shift t by t. t too much. Small t by large t with a period. This is what? Delta t minus 2t. Because they shifted by 2t. From here, they shift 2t. And they keep on going on. How about this? Delta t plus t. They're shifting by minus t. You got it? And then, if you add them together, they will be our impulse train, which is, you can think them as, okay, delta t minus large t having integer times from k equals minus infinite to infinite. 1, 0, 1, 2, 3, 4, minus 1, minus 2, minus 3. Then you can add them all of it. Then this one is here. So this function represents the delta function happens every period of t starting from 0. That's how we define it. Question? So question here is, so this is our problem. This is our problem. This is our problem. Let's find out Fourier series coefficient of this. How we first start with. Of course, we can say, okay, let's do it. This is our x. This is our x. Let's put them inside integration over a period dt. And then what do we do? Let's calculate. Say that you should define like this. You may do it like this. So this one don't have any relation with the t. So let's take this one to outside. Get this one to outside. And then what? And then let's define delta. Say, okay, this one is not 0 only when t equals kt. Right? So now we use this. This can be typically minus t to t over t. But we do not lose our generality if we just add it. If you just add kt. And then we divide this one to say, all right, when k equals 0, that means delta t times exponential minus 0, k is 0, dt, over a period which is from here to here. So say, so from here, k equals 0, so minus t from over here. What was the second one? Delta t minus t, k equals 1. Exponential minus j omega 0 t dt over a period. Now our case 1. Our case 1, that means t minus t over 2, t plus t over 2. You calculate it. You keep on moving on until you find solution, which is somehow consume some time. You can find solution somehow. You can do that, no problem. But it somehow takes you a lot of time. So let's think about, is any way we can simplify this problem using the property we learned before. So once again, in Fourier series, what we learned is using the definition, we find ak at each k and try to find the Fourier series. However, in many cases, we can simplify our calculation using the property we have learned before. So let's see how we can apply our property. So this is a calculation, you can do it. Of course you can do it. I'm not saying that this is wrong. This is absolutely true. You can do that. No problem. But what if you can simplify the problems? How we can do it? So when you see this, let us change the slide to go back to our property here. Let me erase this one for a minute. And let's see this x function and see that if you can apply any of our property. Let's see. This one is basically addition, adding multiple variables. So we can think them as linear, right? So let's bring our linear property. Linear property is what? We can divide them, say, we can divide them into delta t minus t, and then find Fourier series of each of it, and then add them together. Then we still can find Fourier series coefficient. That's a linearity property we have. What else we can use? What else you can use? This one and this one, let's compare these two. This one and this one has a relationship that they are shifting in time. We are moving delta to t, 2t, 3t, minus t, minus 2t, minus 3t. We are shifting the delta function to by t in time domain. So you are shifting in time. What's the property in time shifting? There's time shifting, right? Time shifting, second one. So what is it? If we shift by t0, then we have original one multiplied by e minus j k omega 0 k t0. So property here is if you have xt minus t0, their Fourier series relationship will be ak e minus j omega 0 k times t0. That's the property. So we can think them, okay, using the linearity, we already know that if you find the Fourier series coefficient of each of it, if you add them, you can find a solution. using this, say the Fourier transform of A delta is AK. Assume that the Fourier series coefficient of delta is AK. Then what is the Fourier series coefficient of delta t minus t? Now our t0 becomes t, so you can think that okay, t0 equals large t. And what's the property? AK exponential plus or minus j omega doesn't change, j omega 0, k doesn't change. What is our t0? Large t, right? What about this? If you have delta t minus 2t, that means our t0 is 2t. Therefore, if you already know AK, which is coefficient of when delta, we multiply them by E minus J omega 0 K, which does not change, but our T0 changed to 2T. Right? Of course, if you have delta plus, if you have delta T plus T, then its Fourier series coefficient will be AK times E minus J omega 0 K, which does not change, but our T0 will be minus T now. So that will looks like plus J omega T, KT, like this. So you can think that the Fourier series coefficient of this one, if you do the Fourier series, there will be looks like something AK times exponential minus J omega 0 K, which is the same, but this one changes. Say this is M. M changes from minus infinite to infinite. Right? We use proof properties. We used linearity. We used time shifting. And if you find AK, only AK, then you can find a solution. You don't have to calculate all of the integration. How do we find AK? AK is what? Fourier series coefficient when delta is x. So what is it? Say we are integrating from minus t over t, which is the first one we derived before, and they become, this one becomes what? This one becomes 0 except t equals 0 and t equals 0. And then what? When t equals 0, we have a period delta t, and t equals 0, this one becomes 0, right? T equals 0. Then this one becomes 1. So therefore, there becomes what? 1 over t. So you can find AK. You can find AK, which is right here. So in here, all of this one becomes 1, and this one becomes what? This one becomes 1 also. Therefore, the one becomes like this. So you already calculate what is AK. AK is 1 over t. If you put 1 over t over here, then this is our solution. This is our new AK, say that. Or new AK, Fourier series coefficient of this x. So in short, if you use the property, using linearity, you separate them and find the Fourier series coefficient of each, and then from this relationship, you figure out that this is a time shifting version. Using time shifting property, we multiply them by e j omega 0 k t 0 and find t 0 is large t. So if in here, if you know AK, one calculation, one more simplest calculation, if you did one calculation, then you can find everything. The output of AK will be 1 over t, which is here, times e j omega 0 k t 0 actually. But t0, I'm sorry, here is a we need a large t. In t0 is actually found to be integer times t. 0, t, 2t, minus 3, minus 2t. So we can show them like this. If you only do the one calculation of xk, which is t0, then you can find Fourier series coefficient without much effort. That's the beauty of why we are learning the property. Question? Let's bring in another example, have a different thing, a little bit slightly different one. Slightly different one. In here, I will not do the detailed calculation, but show you how we analyze the problem. So before that, we have this impulse. Now, the question here is, okay, here was 0. We have, here is t1, not period, minus t1, going down. This is repeating at every t. Could you figure out the difference? In this second example here is, set is this. This is a set. They are pointing up, pointing down. There's a sequence. And they have, from the center, they have a spacing of t1. All right? In here, there's only one impulse at the center. In here, they have two impulses shifted a little bit. And then this is repeating at every t. So in here, the spacing will be t1. So this value will be t minus t1. This value will be t plus t1. Likewise, this value will be 2t plus t1. This value will be 2t minus t1. All right, so they keep on repeating plus and minus sign. First thing you have to figure out is what is repeating signal. What is repeating signal? What is repeating signal? It's up and down. And you put a bracket. Say, you can do it either way. Of course, one way you can do it is, okay, minus t over 2, this may be typical. But for one period, this is our repeating signal. Or you can pick like this. You can pick like this. Or this red box, from 0 to t, they are pointing down, pointing up. You can do that in yellow, you can do red, whatever you want to do. Just take a bracket, take a box, which one is repeating, and keep on repeating. How you can find it? How you can find it? Assume that we have yellow in here. Then there will be looks like this. Delta, this one, is what? T minus t. T plus t1. They shifted to minus direction by amount of t1. What about this one? The delta shifted to positive direction by t1, but they have a minus. Right? Once again, the original delta, they shifted to minus direction by t1. So they're like this. This one, the white one, this one shifted to positive t1, and then reversed. So we put the minus in here. So this one defines this and this. And then we know that this one is repeating. This one is repeating by a period of t. So we can think them as they are repeating by t. And add them from minus infinity to infinity. 0, 1, 2, 3, 4, t, minus t. I'm not telling t1, here's t, period. Minus t, 2 minus t, 3 minus t. So okay, keep on like that. So we can define the function like this. Likewise, before, we can think them, okay, they can be this set. Say this is set. This set, when k equals 0, k equals 1, k equals 2, k equals minus 1, they add it up. If you find the Fourier series of each of it, then you can find the solution, which is the same claim we had before. And what is each of it? Then they will be shifted by 0, shifted by minus t, shifted by minus 2t. So this time-shifted version, which is similar to what you have just before, like this. The time-shifted version of this set. Now the set is 2, pointing up and down. So how we do it? We only have to find out ak. Remember the previous case, we find ak in 0 when delta t and find the solution. In here, the delta becomes, instead of delta, we have delta t minus t1 minus delta like this. How do you find it? We can still use the same property, right? This one is time-shifted version of delta, right? So to find Fourier series coefficient of this, you can calculate that what is delta? Delta 1 is Fourier series coefficient of this. This is time-shifted version by plus delta t. So we have exponential j omega 0 k what? t1. And then this one is what? This one is what? t over 1 e j omega 0 t1 minus. Because of time shifting property. I'm sorry, I left k. Right? And then this is plus, this is minus, so put minus between them. This is Fourier series coefficient of this. If you add this one, shift by e minus j omega 0 k mt. If you add all of it, that's the solution of this. Do you find the logic? So you first figure out what is repeating. Define what is repeating. Because Fourier series coefficient always repeat. You cannot find Fourier series coefficient if it's not repeating signal. If it is repeating, let's think about how to represent the repeating signal. Find the basic signal, which is this and this in here. Put this one to represent the those shifting. And those shifting always go to time shifting, which is exponential minus j omega 0 k integer times t. And then find Fourier series coefficient of basic signal, which is the Fourier series coefficient of the original shifting bracket. And that will look like this. And this one you can solve it by yourself, or you can find something more simpler, which is we already derived. From here, you can still calculate it. So this claim is still very useful to simplify your calculation.